We're going to look at periodic functions in two parts. This first little picture shows a cycloid, which is the path that a point on the edge of a circular wheel follows as the wheel moves along the straight line. So there's a light attached to this front tire here, and it's moving, and the light obviously follows that path there, and that would be considered periodic. So the period is the smallest interval of the domain in which the function does one full cycle. So you want to get one full cycle. We really could have said this is periodic from, I don't know if you can see that drawing, from here to here, but that's not the smallest interval. So let's go ahead and look at an example here to kind of get us thinking in terms of periodic functions. Give the graph, period, domain, and range of the function, and then express it in simpler form. So f of x equals, and it equals 2 sometimes and negative 2 sometimes, and then 2 and negative 2. So we're going to graph these and see if we can see a pattern, and then we're going to state these different things that are mentioned. So f of x equals 2 if negative 3 is less than x, which is less than negative 1. So we want this graph up at 2, but we only want it from negative 3 to negative 1. So in this interval here, this just helped me see the interval. You don't need to put these on your graph. And we want it to be 2. So we go from negative 3 to negative 1. We want our graph to be at 2. And they're both open circles because they're just the less than signs. And then we want the graph to be at negative 2 from negative 1 to 0. So we have negative 1 and 0. And so the graph is at negative 2. Put the circles here. From negative 1 to 0, it's going to be y equals 2. Both of those circles get filled in because it's got the or equal to. Then it's back to 2 again from 0 to 2. So in this interval. So it comes up here. Open circles. So we just did that one. We can come down to negative 2 from 2 to 3. So from 2 to 3, we want our graph to be at negative 2 again. And it looks like it keeps repeating this pattern. Back to 2 from 3 to 5. So from 3 up to 5. And then negative 2 from 5 to 6. And I think we can see what's going on here with our pattern. So to the far left here of our graph, it would actually come down here. And then back up. So what is the period? Well, the period is how long it takes to do one full cycle. Well, one full cycle looks like it's getting the 2 and the negative 2. So we can start here at 0. So all the way, that yellow part is one full cycle because then it goes back up to the 2 again. And so our period is 3. Starts at 0, so 1, 2, 3. So the period is 3. Domain. Domain. Looks like it takes up all the real numbers. I know there's open circles up here, but those x values are used down here on the negative 2. So it's all real numbers. The range, what are the y values this gets to? Well, only negative 2 and 2. Express it in a simpler form. So instead of having this dot, dot, dot at the beginning and the end, we want to try to write f of x in a simpler form. So f of x equals, well, only ever equals 2 or negative 2. So 2 or negative 2, and we're going to try to generalize what's happening here. So what we do, and actually I have it down here, express a periodic function in a simpler form, determine the period n, well, our n was 3, and we're going to multiply that by a constant, k, and k is going to be just any real number. So we have 3 times k, and we do is less than x is less than, and what we do here, it says start by using the interval that includes 0. So the interval that includes 0, there's 2 that include 0. The one that includes it is down here. I'm actually not going to start with that. I'm going to start with the one that goes to the right of 0. So if I put, sorry, I'm going to have k, where k is an integer. I think before I said it was a real number, but k is going to be an integer. So 3 times 0 would give me 0. So I'm trying to figure out how to get this first, not really the first, but this one that has the 0 in it. And so we think, what if k were equal to 0? That would give me 0. If k, how could I get 2 here using the 3k when k is 0? Well, that would be 3k plus 2. And then, so again, the 3k, if k were 0, that would give me 0. So I don't have to add anything to 3k if k was 0. That would get me this spot right here. And then I had to add 2 to get the end of this interval. I have both less thans. I don't have less than or equal to because they're open circles. And when did it equal negative 2? Well, equal negative 2 starting at 2 and going up to 3. So I can still take this, still thinking k is 0. That's kind of our reference point. How do we get to 2? Well, if this k was 0, it would be plus 2, which oftentimes these are the same. Is less than, I'm going to put or equal to, because it's got the closed circle, x, which is less than or equal to. And how do we get 3? Well, we have the 3k. If k were 0, we would have to add 3. So 3k plus 3. So that is a simpler form. We can kind of try this out if we wanted to see if it works. Let's say we put the integer negative 2. So if k equals negative 2, 3 times negative 2 is negative 6, plus 2 is 4. So negative 4 should equal negative 2. 1, 2, 3, 4. There it is. It's at negative 2. So there's the simpler form. Here are a bunch of periodic functions, and it said state the period of each. And we're not going to do all of these, but this one here looks like the period is from here to here. So the period looks like it's about 5 because it's a little before negative 1 up to a little bit above 4. So the period would be 5 from negative 1 to 4. This next one, can't really see the numbers very well, but here's the period from here to here. If this is counting by ones, this would be 1, 2, 3, 4, 5, 6. This would be a period of 6. This period looks like it repeats every 2. There's an interesting graph. This says pi, 2 pi, 3 pi. So if I start here at 0 and I travel along here, when do I get back? So I get back to 0, but does it look the same? No, now it's going downward. So here is where it starts to look the same at 0. So that part I just traced over would be 1 period. And so that period here for this one is 2 pi. This next crazy one, kind of looks like maybe here, but no, because it goes down and it goes up even higher again. These kind of match, so our period would be 4. This one, I think this says pi and 2 pi. So this one This would probably be half pi. So in one little branch here, this is in several different parts, but this one goes from negative pi over 2 to pi over 2, so the period would just be pi, because that's like half, negative half to positive half. It would just be 1. So we'll stop there. We could keep going, but we could find the period of these different ones. That's it for the first section.